All right, next on our journey through quadratic time sorting algorithms is insertion sort here. So insertion sort works by dividing the sequence into sort of two halves here. The left half is stuff that we've already sorted, and then the right half is stuff that isn't sorted, right? It's sort of unsorted there like that. So the idea is we're going to grab the first value in the unsorted section here. We're going to grab the thing at sort of index I there. And then we're going to figure out where it should go in the sorted section, and then we're going to insert it there. So in order to take the 3 that was over here, let's get back a step, right? To take this 3 and insert it between the 2 and the 4, I have to push the 4 and the 6 up, and then put the 3 in the middle there. So that has the effect of expanding the sorted section by 1 while shrinking the unsorted section by 1. So of course, if I just do that over and over, right, eventually the sorted section will expand to cover the entire sequence, and the unsorted section will shrink down to 0 there. Now, how do we start this process? Like, what does it look like at the very beginning? You might expect that we'd start with the entire sequence being red, the entire sequence being unsorted, and that works fine, like you can do that. But remember that a sequence of length 1 is sorted, right? If I give you the number 12 and I'm like, hey, sort this, you're like, I'm done, right? Like, one thing by itself is sorted. So we can, in fact, grab just the first thing in the sequence and claim that that is already sorted. And then the unsorted section is the remaining n-1 elements after it there. So that means our outer loop is going to start with I equal to 1. So you might have already written the code to actually do the insert in assignment 1, in the sort of ordered array stuff there like that. But it's worth thinking about the most efficient way to sort of do this here. So there's two possibilities. We want to insert a value x into the sorted section, which is sequence 0 through I-1 there like that. So one option would be we could basically do 2 loops, right? We can start at the beginning and scan forward until we find something greater than 3. So we would stop here at 4, and that tells me that the 3 should go before this spot there like that. Then we do the shifting to move everything after that spot up and make room for the 3 there like that. So I have a loop that starts at index 0 to be like, all right, where's this 3 go? And then I have a loop that starts at that spot that moves everything up to make room for it. If I do that, I am looping over the entire sorted section every single time there. So that would make this not adaptive if we use that method. Another option, though, would be that we could start at the end of the sorted section and pull the value down. So I could grab the thing and sort of drag it down here. So I would basically say, oh, 3 is less than 6, I'm going to swap those. Oh, 3 is less than 4, I'm going to swap those. Oh, 3 is greater than or equal to 2, that means that's where the 3 goes here. So I grabbed the 3 from here and pulled it that way here. So note that this method, right, I only drag things as far as necessary. I'm not looping over the entire sorted section. I'm only looping over the part of it that I need to drag the 3 or whatever into the correct position here. So if I use this version, if I work right to left, that's going to make my insertion sort adaptive here. So here is the code for insertion sort here. So over here, I is just keeping track of the beginning of the unsorted section here. So this is the start of the unsorted section is what I represents. All right. So at the beginning, index 0 is sorted, index 1 and up is unsorted there like that. So I want to grab sequence at index I and insert it into the sorted region, which is everything before that there. So I start at I, right? I'm at some index I, and I'm going to move down. I'm going to decrement j here, dragging by swapping the value down there like that. If the jth value is less than the value before it, this is like a reverse compare and swap from bubble sort here. Then I swap them. But if it's greater than or equal to, right, that's what the else part here means, is that the ith value is greater than or equal to the value before it. which is what we want. That's what it looks like when it's sorted. Then we break. That means we've dragged the thing down to the correct position there, so I can stop that like that. So the best case is if it's already sorted, then the J loop just breaks immediately every single time. So we do O of n time in total to kind of like look through all the stuff there like that. The worst case happens if it's sorted in descending order. So then I have to drag everything down to the beginning, and that's going to take me O of n squared time to sort of do that work there like that. In the sort of next one, we'll see a variation on insertion sort called gnome sort that is kind of like a little bit sort of fun there like that, right? But notice that because like the J loop is going in this direction, it's going right to left, we can't do an insertion sort on a singly linked list because singly linked lists don't let us go backwards. A doubly linked list would be just fine though, like that. That would work just fine there like that. So insertion sort is kind of like a where do you go type of sort, figuring out the order of the elements relative to each other, but everything is sort of stable until it sort of hits the end here. So it has a worst case runtime of n squared, like all of these that we're talking about right now. It uses a constant amount of memory because it's an in-place algorithm. It's adaptive because we have that break in the inner loop there like that. And because we don't swap things that are far apart, it is stable, like it's safe to use in a multi-stage sort here. Insertion sort is usually agreed to be like the best of the quadratic time sorting algorithms here. So it's kind of like the fastest in practice. For small sequences, remember that the big O only applies when n is sort of like big enough here. So if you have a small sequence, insertion sort may actually be faster than some of the other like algorithms that we're going to look at later that are theoretically better here. So that means that like, you know, it's not that like these n squared algorithms are useless. Like if your sequence is short enough, insertion sort may very well be the fastest way to sort of sort it there. So we'll see insertion sort come up later, even when we're talking about sorting algorithms that are faster than n squared, as like a thing that is still sort of useful there like that. All right, that's it for insertion sort. Next up is gnome sort.